Okay, let's work an example number 2. And in this one, we are going to work a 3-variable example, which is a xyz function. In this case, maybe the dependent variable could be w, but in this case, the dependent variable is, in this case, is t. T is the dependent variable, and t is a function of x, y, and z. For this example, the variable t is expressed in degrees Celsius, and the x, y, z terms are expressed in meters. So let's suppose that we have some temperature in a point in a 3D space, x, y, z. So there's a specific point in this space, and the temperature there is given by this function t. This is equal to 80 divided by 1 plus the value of x squared plus 2 times the value of y squared plus 3 times the value of z squared. So this is the expression that will give us the temperature in any point in a three-dimensional space. So if we want to know, for example, if x value is 2, the y value is 4, and z value is 4, substitute here x, y, and z, the values in meters for that specific point in space. You perform this calculation and you will know what's the value for t. Okay. Well, the question is, in which direction in the three-dimensional space does the temperature increase faster at the point, let's say 1, 1, minus 2? So we are in the 3D space and we are in this specific point. In what direction the temperature is going to increase faster? What is the maximum rate of increase for the temperature in that three-dimensional space? Okay, those are questions that we can answer applying the partial derivatives and using the gradient vector and the directional derivative. Because we might know that maybe it's not in the y direction, or straight in the x direction, or straight in the z direction. So it could be any type of direction according to the vectors, and in this case, the gradient vector. Okay, so let's start to work this example. And the first step is to calculate the gradient vector of the function. As you know from the previous lectures, the gradient vector for T, which is the temperature, is going to be the partial derivatives of T with respect to X times I, plus partial derivative of the function T with respect to Y times J. This is the Y axis. And partial derivative of the function with respect to Z times K. Okay. Using this guy over here, we will end up with this partial derivative of the function with respect to x is equal to this, with respect to y is equal to this, and with respect to z is equal to this. So you might be asking, how can we get these results? Well, let's make here a big parenthesis. Let's write that with parentheses here. Big parentheses. Let me rewrite that because means that this is something related to that one. So let's just do a parenthesis here. Okay, just to as a refresher, let's calculate the first one. So we can, from the first one, we can get the other two. Okay. So we need to calculate the partial derivative with respect to x of this function, which is 80 divided by, in this case, 1 plus x squared plus 2y squared plus 3c squared. Okay, and we want to know the partial derivative of this, which is this very first one, this the one that we are going to work. Okay, here we have a constant value, so we can move the constant to the left, and let's say we have now 80 times the derivative of the function with respect to x of 1 over 1 plus x squared plus 2y squared plus 3c squared. Okay, so now we have that that function. Okay, sometimes it's hard to calculate this derivative using the quotient rule. So it is better for us if we do a substitution here. So let's say that this is equal to u, this function. Let me this and let me write here the equal to u. Okay, so we have now that now is the derivative of this is going to be equal to, let's say, 80. Let me rewrite that, times the partial derivative with respect to x. Let me write this as x squared plus 2 times y squared plus 3 times c squared to the minus 1. So this is how we can get rid of this numerator here and denominator. So we can change that with u. So that's going to be equal to u to the minus 1, which is this part, u to the minus 1. And this 80 is a constant, so we keep that on the left. And now we have this a little bit easier to deal with. Okay. So now um, the value that we are interested in is in this one, because this is the x squared. All the other guys is going to be treated as a constant. So we can, here we have two types of function, because we have this inner part, and now we have this inner part going up to the minus 1. So we have a product of functions. So we need to play the chain rule. Let's write here chain rule. Let's apply the chain rule, and that is going to be equal to 80 times the partial derivative with respect to x of u minus 1 times the partial derivative with respect to x of the inner part. Okay, and this is because we have this inner part there. So we need to apply the chain rules, which is the outer derivative times the inner derivative. Okay. Oh, so now the first part is equal to, let's see, the partial derivative with respect to x of u to the minus 1 is equal to minus 1 divided by u squared. Okay, comma, and the partial derivative with respect to x of all this large expression here plus x squared plus 2y squared plus 3z squared is equal to 2x, because all those terms are considered constants and we are going to differentiate with respect to x, and the only value of interest there is the x squared. So now we have the first part, which is the outer part. This is this that is going to be substituted by u, and the derivative of the other part is 2x. Now we need to calculate the product of these two. So that's going to be equal to, let's say, let me erase here just a little bit, and let me extend this parenthesis here. So this is going to be equal to 80 times minus 1 divided by 1 plus x squared plus 2 times y squared plus t times c squared, because here it is, times 2x. This 2x is this 2x here. So this is the expanded expression for this. Remember that u is equal to this. And this is the derivative of the inner part. So if we simplify this, we will end up with a result that the partial derivative of respect to x is equal to 160x divided by 1 plus x squared plus 2 times y squared plus 2 times c squared squared. And this is the result of the first one. Okay, this is more kind of how to get the partial derivatives. So this is the first one, and you can repeat the same procedure if you want to get all of these other two. So now we have clear how to get the partial derivatives with respect to x, with respect to y, and with respect to z. If we factorize this, we can have, because this is a common number for this, we have here a common multiplier, so we can factorize this as 160 divided by this times minus x by x times the ith component of the vector minus 2 times the y component of the vector minus 3 times z times the z component of the vector. So now we have this formula here. Now the next step is to evaluate the gradient vector in the points 1, 1, -2. And if you do the substitution on these two expressions, this is equal to 160 over 256 times the, this vector. And simplifying these calculations, we will end up with this 5 over 8 times minus I minus 2 times j plus, say, 6 times k. And this is the gradient vector evaluated in these points. So to answer the question is, in which direction does the temperature increase faster at the point 1, 1, -2? This is the direction in which the temperature goes faster. Why? Because this is a vector. So this is going to be the direction. 5 times these components of x, y, and z. Another question will be, what's the rate of increase of the temperature at that point? If we want to know that, we can calculate the modulus or the magnitude of the vector at this at that point. And if we do the calculations of the magnitude of this is equal to 5 times the root square of 41 divided by 8. So if we perform the math here, you use your Casio calculators, you will end up with this operation that is something like 4 degrees Celsius over each meter. Okay? That's the rate of change at that point. So you move a meter in some direction, in the direction of the gradient vector, you will experience a change of temperature of every meter. You're going to experience a 4 degrees Celsius by every meter that you move in the direction of the gradient vector. Okay. So this is a brief example of a practical application of the partial derivatives in the real world. As I said before, there is a lot of other examples that you will be required to perform if you are going to keep working in the engineering field. So please take note of this and practice. I hope to see you soon, and take care.